Welcome to another episode of Learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held on February 28, 2025. In this video, we discuss the solution of a problem from the section Linear Algebra, and the problem is related to the dimensions of certain subspaces. This question is placed in part B, which is a multiple choice question, and it carries 3 marks. The question ID is 704107. This question is suitable for all these examinations. Right. The given question is, let U denote the span of the set consisting of e power t, e power 2t, e power 3t in the real vector space of continuous functions from the set of real numbers to itself. Consider the R vector spaces. Capital V is equal to the set of all F from U to R, where F is an R linear transformation. V consisting of all linear transformations F from U to R. W is equal to the set of all F belongs to V, such that f of e power 3t is equal to 0. Which of the following statements is true? We are given 4 options. Option 1, both v and w are infinite dimensional. Option 2, dimension of v is equal to 3 and the dimension of w is equal to 1. Option 3, dimension of v is equal to 3 and the dimension of w is equal to 2. Option 4, v is infinite dimensional and the dimension of w is equal to 0. Right. Let's now discuss the solution of the problem in detail. Right. Here is the given problem. We have C R comma R. This is the notation for the real vector space of continuous. C stands for continuous functions from R to R. Given U is a subspace of C R comma R spanned by the set consisting of 3 functions e power t, comma e power 2t, comma e power 3t. That is, U is the subspace spanned by this, means U is the linear span of e power t, e power 2t, e power 3t. Obviously, it will be a subspace of C or R. And U is spanned by this, and it is very easy to see that these 3 functions, e power t continuous functions, e power 2t, e power 3t, this set is linearly independent over R. This set is linearly independent and U is spanned by this set. Therefore, this set is a basis for U. Therefore, the set e power t comma e power 2t comma e power 3t is a basis of u, and so the dimension of u over R is the number of elements present in this basis, that is 3. Given V is the set of all R linear transformations F from U to R. It is denoted by the set of all linear transformations from U over R to R over R. This is the notation. This notation we have studied, that is LUV. What will be its dimension? So its dimension is given by, let V and W be finite dimensional vector spaces over the same field F of dimensions n and m respectively. Then L of V comma W, it is the vector space of linear transformations from V to W. Capital L stands for linear transformations from V to W, and it is finite dimensional. It's also and has dimension mn, that is dimension of V over F multiplied by the dimension of W over F. So here in our case, the dimension of V is the dimension of L of U over R comma R over R. That is equal to the product of the dimensions of these two. So dimension of U over R multiplied by the dimension of R over R. The dimension of U over R we have already seen, that is 3. The dimension of R over R is one dimensional, that is into 1. That is equal to 3 into 1, 3. So the dimension of V is 3. So one part we got it. Now given the subspace of V, that is W, the set of all R linear transformations F coming from V such that F of e to the power of 3t is equal to 0. So there is a restriction. There is a restriction on F's. So F of e to the power of 3t is 0. E to the power of 3t is a basis element, and F of that is there. So now let's recall the dimension of a subspace W of a finite dimensional vector space V is equal to the dimension of V minus number of linearly independent restrictions or equations defining the subspace of W. That is, dimension of W is equal to dimension of V minus number of linearly independent restrictions. Here we have one linearly independent restriction, the elements of W are none other than the elements of V only. Therefore, the dimension of W will be the dimension of V minus number of linearly independent restrictions, and we have one linearly independent restriction, that is F of e to the power of 3t is equal to 0. Therefore, 3 minus 1 is equal to 2. So thus dimension of V is 3 and the dimension of W is equal to 2. Let's look at our options. In our options, our answer dimension of V is equal to 3 and the dimension of W is equal to appears, as the option 3. Therefore, option 3 is true and the answer to this question is option 3. That is the detailed discussion of the solution of this problem from the section linear algebra related to the dimensions of certain subspaces. And it is definitely an easy problem, right? I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. I am sure that we are going to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.